Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. Um, I'm looking at myself. I'm looking really unkempt these days. I think the beard needs to go after this. I'm just kind of realizing that for the first time. So do excuse me on that. Hopefully I'll make it up to you with a good explanation to how to solve problem 295. Find median from data stream or data stream if you prefer. In the past 6 months, Amazon, Facebook, Google, Microsoft, Apple have all been asking this one. I think it's a truly great problem. It's a really cool problem, and the solution is just as nifty, but also tough to come across and to understand. And so I thought this would make for a really good video. As always, if you have any specific questions or recommendations, comment my comment is down below. My contact is down below in the description is what I meant to say. Now, the problem begins by actually defining what a median is, which is the middle value in an ordered list. And so if the list is of an even size, I think this is all like middle school stuff, even elementary school stuff. But just to recap, if we got a list of even size, we take the average of the two middle elements. Otherwise, if it's an odd length list, we just take the middle element and return it. For instance, in the list 2, 3, 4, the median is 3. Whereas in 2, 3, the median is the average of the two middle terms, 2 and 3, divided by 2. We want to design a data structure here that will support two operations. So we need to define a add num method, which will add an integer number from a data stream to a data structure, fine. And then the find median, and that will return a double. So this one is going to return it's going to return nothing. It's a void function. Second one will return a double, or if you're in Python, a float. Tomato. It's going to return the median of the elements so far that we have. Pretty straightforward ask. The solution is not straightforward though. And also we've got a constructor here since we are creating this kind of new data object. We will have to initialize some sort of constructor and tell this thing how to behave. Let's say that I'm running with a really simple example here of 1, 2, 3, 4, 5, 6, and what I'm doing here is, not that I'm simulating a data stream, but imagine we were getting these numbers fed one by one, and at any given point, somebody can ask us what the median is of what we have so far. If the numbers came in this order, it would be pretty simple because we just got a list here, and we'd end up finding the average of these two numbers and return 3.5. Now, what if these came in some random order? We got maybe 5, 4, 2, 3, 1, 6, and I'd encourage you to, if you're not sure right off the bat, maybe to pause the video and to tell me what the naive solution would be here, which is worth mentioning. But the naive solution would be to just take these numbers and every time you add a new number, sort it. So you'd have some sort of n log n solution where you're storing the n numbers in a list. And maybe, let me correct myself. Instead of sorting the list every time, when you're asked for the median, you can then sort the list and then return it, again, quite simply. I think finding the median is kind of the trivial piece here and just returning the middle element. But the basic approach being store all these numbers in a list, sort them, return the middle number. That's a good naive solution just to begin with, and it's worth mentioning. But chances are we can do better. And so if you think about this for a second, and if you haven't really tried this problem much already, I would encourage you to pause the video, but think about what data structure can we use that keeps some sort of semblance of order as numbers are coming in. Okay, for those of you who are strictly Python, who are non-Python based, maybe if you're focused on JavaScript or another language that doesn't have a built-in heap structure, this may not come intuitively to you, but heaps are an excellent tool to use in problems like these where we need to, again, keep some sort of semblance of order of numbers coming in. And so the trick here to this problem, though, isn't just actually acknowledging that we need to use one heap. It's the fact that there's a really cool way to do this using two heaps, and let me show you guys how. Imagine that I had two heaps. One heap was a max heap, and the other was a min heap. Okay, let me show you guys what I mean by this. And let's assume that I was getting these numbers in from 1 to 6 in some sort of stream order. And what I had to do was to keep one half of the numbers in one heap and the second half in the other heap. Namely, I'd want to keep these, let's say the three smaller numbers in one heap, and I'd want to keep the three larger numbers in another heap. Well, get this. What I actually want to do is to take the bottom half, so the smaller half of the numbers, and keep them in a max heap. And so what I'd have is a heap that resembles something like this. So in the max heap, the largest number is at the top of the heap, and it's accessible in constant time. Whereas with the min heap, I would want to keep the smaller number on top, or the smallest number, excuse me, and the 5 and the 6 would be children in no particular order. The way that these heaps work, remember, is that when we're adding an item to the heap, it takes log of n time to compute and to add it to the heap. Accessing the top element is a constant time operation, but overall, keeping something like this sorted, or at least knowing what the top element is a log of n operation. Or again, accessing it is constant time, but adding numbers in or removing them is a log of n operation. Why is that important? The important thing to notice is really the crux of getting to the bottom of this is knowing that we don't actually need to have this entire list sorted. Okay, that is false. We don't need to keep the whole thing sorted. What we need to know at any given point is what the middle element is, or what the middle elements are if there are 2 of them. That's it. I don't care if we have a 2 and a 1 here, or if this was a 1 and a 2. It makes no difference, because as long as I've got this half of the array split up into lower and upper half, check this. As long as I have it split up that way, we can see that in the max heap, where we have our smaller elements, my constantly accessible element is one part of kind of the middle of this entire array from 1 to 6. And on my min heap, or where my larger numbers are, the smallest possible number, this 4, is the other half, right? I've got instant access to these 2 numbers. So what I do is I say, if I've got 2 heaps of equal size, just grab the top element from both, add them up, divide by 2, and return it. This would return 3 plus 4, 7 over 2, 3.5, okay? And that's how we deal with this if we've got an even number array, even length. Let's say that we had this 6 wasn't here, and this is what I had. So I only had 4 and 5 here. In this case, I can say just go to my max heap and grab the top element, which is the middle number here. So this will just be the 3 here, because we have an odd length of numbers in the stream, okay? And so that's a key thing that we really need to notice. How we're going to go about balancing these 2 trees is going to be its own kettle of fish. So I will get to that kind of in more so the latter half of this video, because that's really not trivial. But the key thing to understand here is that I need to initialize 2 heaps, a max heap and a min heap. The max heap will, so let me kind of write this down. Maybe I'll say under these conditions, I'll say max heap will contain, I'm going to say max heap just like this for short. It will contain smaller half. Or maybe I'll say smaller half of the number. So smaller half, you guys know what I mean there. I'm going to instantiate a minimum heap, and that min heap is going to contain the larger half. So that's going to contain the larger half. And what I'm going to want to do in order to have this very nice property where I can just grab the top element and they're always kind of, each of them is taking one half of the array, I'm going to need to get clever about keeping true to the size that we want. So what I'm going to need to do is they're going to need to be same size. So they're going to need to be the same size, or, and here you have a choice. You can either pick the max heap or the min heap for this. I'm going to choose the max heap. So I'm going to say, or the max heap, maybe I'll just say the length of the max heap can equal the length of the min heap plus 1. So meaning we can have one additional element in the max heap. For instance, if we come across this scenario where we have an odd number, I will simply grab an odd number of elements, that is, I will simply grab the top number of the max heap. Again, this part right over here, this is the really tricky part. And so what I'd actually like to do is to implement this part so far that we have is just 2 heaps and then returning based on the length of the heaps. That's really trivial. It's a very small amount of code. So what I'm going to do is I'm going to quickly jump into the code. I'll show you how to implement that, within just a minute or two, and then we'll come back and kind of discuss creating this mechanism for this method over here, the add num methodology. And so I know I don't usually do this, but I think for this video it's appropriate just to kind of almost modularize not only the code but really the idea here within the video itself. What I'd like to do is I'm going to just create a max heap here and a min heap. Now, one thing that I will ask you to bear with me for those of you familiar with Python heaps, you'll know that we need to call a heap queue library and then heapify both of these heaps individually, or both of these lists. So originally they're lists, so we need to heapify them to create them as heaps. That's heap queue.heapify min heap. And what you'll know is that heapify automatically creates min heaps. let's pretend for a second that the max heap will just be a max heap, the min heap will be a min heap, and within this add num function, we'll get a bit clever on how we're returning items and actually, creating the max heap to really be a maximum heap. But let's just pretend that they behave how we want them to for now, even though under the hood, as things stand, they're both min heaps, okay? And then what I wanted to say was if these two are the same, so if we have two heaps of the same size, it means we have an even number of elements in total. So I'll say if the length of self.max heap equals the length of self.min heap, and again, I'm saying lean for some reason, self.min heap, if this is the case, then what I'm going to want to do is I'm going to want to retain, I can't speak today, return self.max heap 0. So that's the top element plus the top element of the minimum heap, and I'm going to divide that by 2. Again, I'm assuming this is actually a max heap. This is actually a max heap. This is actually a min heap. I'm going to grab the top element. I'm dividing by 2 here. This would return an integer. It would be rounded down. This returns a float or a double. Some people you'll see maybe you can do this to explicitly call it a float, but you don't need to here. This will be a float calculation. Otherwise, we said if this isn't the case, then what we'll do is we kind of have this scenario here where we're just going to grab the top element of the max heap. So I would return self.max heap 0, and that's it. Okay. I understand you can also put this logic into a ternary statement and kind of have it as one line. I split it up just in order to keep things readable. So far so good. This is the only code that we need to do for the constructor and for the actual returning of the median. The harder part here is going to be this, is like I said, is really understanding how to add numbers into this heap. And mind you, it'll only be 5 or 6 lines of code, so don't be too freaked out about the implementation. But I don't think that strictly speaking, I don't think that it's an intuitive implementation at all. But that's how we do these problems. We prepare for these interviews so that when you get hit with something like this, you got these tools in the background from all the practice that you've done. All right. Now, there are a couple steps that I'm going to want to do. And here I'll write down the algorithm, then we can do a quick walkthrough and see that it works. So just kind of trust me as we walk through it step by step, and we'll get there in no time. First thing I'm going to want to do is going to be to add an element, or add the element that's coming in to the max heap. Okay. Once I add it to the max heap, the next thing I'm going to want to do is I'm actually going to want to remove top element. I'm going to take the top element from the max heap. So take the top of the max heap, and I'm going to add it to min heap. Add to min heap. Okay. I'm gonna do that, and so I'm looking at my notes here just to make sure that I don't mess this up. I'm gonna remove from the max heap, add it to the min heap. At this point, what might happen is we might have a misbalance, and so that misbalance would occur if the minimum heap, the min heap, had more elements than the max heap. So we said we can't have that. They can either be the same size, or the max heap can have one additional element to what the min heap has. So we'll say I'll say if min heap is greater than the max heap in size, this is implying the length. So maybe let me make that explicit. If the length is different, then what we want to do is we want to rebalance. Okay, and the way we're going to rebalance is by, let me write this down. Then rebalance, and the way we're going to rebalance that is by actually by taking that extra element from the min heap, by taking top element of min heap, and adding it back to the max, and add back to max. Okay, so if you're looking at this and it doesn't make any sense, I understand that, because I understand, like, I get that it seems really unintuitive, and it took me a while to scratch my head over it to really understand what was happening. But let's run with an example here. So yeah, I almost wish that I made this a bit smaller. Let me see if I can somehow grab this and like shrink it a bit. They've added a bunch of new functionality to this. Oh, that's wicked. All right, cool. So I'm gonna keep this algorithm right here. Okay. Oh, here we go. And I go back to the pen. Okay. So let's pretend that I'm getting this data stream. We're going to work with the numbers from 1 to 6, okay? 5, 6. I'm going to keep a max heap. I'm going to keep a min heap. First thing I'm going to do, my first element comes in for the max heap, and I'm going to say this. I'm going to add to my max heap. I'm going to add the element 1. They're both empty so far. I just put a 1 in. I'm then going to remove the top element from the max heap. I'm going to pop it off and add it to the min heap. Now we check, are our heaps unbalanced? Meaning, is the min heap larger than the max heap? It is. If it is, I'm going to take the top element and add it back to the max heap. I know this seems like overkill so far for this first element, but bear with me. Let's go to the second element. It's time for element number 2 here. So a 2 comes in. I'm going to add it to the max heap, meaning that my max heap will now look something like this. I'm going to remove it from the max heap. My max heap is going to go back to being a 1. And I'm going to put it in my min heap. Now, am I going to enter this condition? No, I'm not, because they're the same size. And mind you, I want my heaps to look like this at the moment. The reason I want them to look like this is because I said that my minimum heap is going to store the larger half of the items, right? The larger half of the items from 1 and 2 is definitely just the 2. My larger numbers are in the min heap, so I'm good. I'm happy with that. Now we take one more step, and I'll think maybe I'll do one more step, and I'll leave the rest to you to kind of work out if you don't trust me. But, this will work out. We add the 3 in. We add it by default to the max heap. My max heap will now look something like 3 and 1. I'm going to take it off, add it to the minimum heap. The minimum heap will look something like 3, 2. Now, I've got, is there a misbalance? Yes, there is. So we're back to kind of the first step that we had. Is there a misbalance? There is. I'm going to take the top element of the min and add it back to the max. Okay, so I'm going to take it off the min. Let me make sure that I got this right. I'm going to take it off the min. Excuse me. Okay, that's why I was confusing myself. Once I added it to the min, I added the 3 to the min. We already had a 2. We actually would have a 2, and then the 3 would go down below since it's a minimum heap. My apologies. And this is why this works out nicely. Now when I pop an item off the min heap, this 2, and add it back to the max heap, it's going to go, it's going to go right here. We're going to have a 2 and a 1. And now look what we have. From the 1, 2, and 3, we have this condition that we want, okay, where the max heap is always same size or 1 bigger as the min heap. On the min heap, so our larger half, I've got the 3. Our smaller half, max has the 2 and the 1. And so no matter how many elements I add at every single step, I'm going to have 1 extra element in my max heap, and then we'll add 1 to the min heap. And then we'll add 1 to the max heap, and then to the min heap. And we're going to keep going through this process this way. The reason that we need to take off the top item from the min and add it back to the max is going to be so that we're always keeping, again, the smaller half of items in the max heap. I think this algorithm it's very clever, but it's not intuitive, okay? It's really not like, I'm not sure that it's user-friendly the first time you see it. So if it's a bit uncomfortable to digest, I understand that. It's one of those that you'll have to sit down, work through a couple times, and get familiar with or get a bit more comfortable with because well, it's a very useful algorithm that, like I said, it's not intuitive, right? It's tricky, but it will be useful. So don't panic if it doesn't make sense entirely, but I would encourage you to sit down, code it out, walk through this example by hand, and then I promise it will make more sense very soon, okay? Now, to actually implement this thing or these 3 steps, what we'll do is the following. So we'll go to add num, and the first step that we said we needed to do was to add to the max heap. So what I've got to do is I'm going to say heap q.heap push self.max heap, and in this notation we need to specify the heap we're pushing to and then the element we're pushing in. It'll be num. Fine, we've pushed that in. Our second step was to remove the top element from the max heap and add it to the min heap. So I'll say heap q.heap push. Now we want to add to the min heap. What do we want to add there? We want to add the top element of the max heap. So I want to say take self.max heap and add the top element, and then we'll pop it off. So these 2 items, you can kind of reverse the verbiage of it. Let me show you here. So I want to pop off from the max heap. Yep, I want to pop off from the max heap. You could change the order here. Like you could take this line of code and store it in some sort of like temporary variable. So say temp is equal to this, and then add that temp variable into here. I didn't here, although again, you very well could if you wanted to. Finally, the last part we need to take into account is this rebalancing situation if the length of the min heap is larger than the length of the max heap. So we'd say if the length of the min heap is larger than the length of the max heap, what do we need to do? Well, we need to say, let's take that top element of the min heap and put it back into the max heap. So let's say self.heap push into the max heap. We want to push in the self.min heap's top item, just like that. And then we want to take that minimum heap and whoops, this should be heap q.heap push. There we go. And then what we want to do is pop that element off the min heap. So I'm going to say heap q.heap pop self.min heap. Now, this is all the code that we're actually going to use in this solution. This won't work just yet. I'm going to run it really quickly, but we will get an error. I just want to make sure that I don't have any. Right, so I figured that I'd have typos somewhere. So let me make sure that I get all these selfs in here. Max heap is not defined on line 6. So what am I doing here? Self dot. It's the issue with talking and coding at the same time. Line 13. What did I do? Another typo. Heap pop. Sorry guys, a bunch of typos here, but fine. So we got to the point where our answer just isn't correct, and I'm okay with that so far. The reason it's not correct yet is because, again, like I was saying earlier, by default, Python uses a minimum heap implementation when you use this heapify item. So the tricky part here is to say, well, how do I turn a min heap into a max heap? The way you're going to need to do that is actually by taking every element that you're putting into a min heap, make it negative. Okay, so let's say that I had some min heap that looked like 1, 2, 3. How do I turn this into a max heap? If I made all these items negative, well then my min heap would look like this, something like -2, -1. And so this is still a min heap, but if I'm taking items in, putting items in or taking them out, I just take in and put out the negation of them to get the number that I want. All right, so this is a pretty cool trick that I learned a few months back on how to deal with creating max heaps in Python. So what we need to do is when we're adding items into the heap and removing them, we need to negate them out of the max heap just in order to make sure that that it behaves like a max heap and stores the numbers we want. So what I'm going to do here is if I'm pushing into the max heap, I'm going to store the negative of that number, right? If I want to put a number into the min heap. If I check my max heap, it's got the negative of the number that we initially put in. So I need to negate that. Right here, we're popping off. We're fine. I've got to now push an item into the max heap. So I want to push the negative of the number itself so that our min heap behaves like a max heap. And finally here, when I'm returning a value from the max heap, again the number in the heap is the negative of what we want. So I need to negate it. And same thing here. We want the negation of what we put in. And now if I run it, we should get the correct answer. And I'm going to hit submit here. Hopefully the runtime is favorable. It is. All these runs, like don't worry too much about the runtimes here because the solution is an O of n log n solution. It's a logarithmic solution because at most we do 1, 2, 3, 4, and 5 operations to a heap. So either pushing or popping, which would be 5 times log of n or log of n every time we need to add a number. When we're actually finding the median, that's constant time, and so overall the time complexity we'd have would be log of n. The space complexity would be O of n because we're out of all the numbers that are coming in from the stream, we're storing half of them, so n over 2 kind of in one heap and n over 2 in the other heap. Overall, that'll be O of n storage space. And that's it for the question, guys. So again, super tricky because we got to use 2 heaps. We got to figure out a way to balance them. There's another way to solve this. Well, using a self-balancing binary search tree. But I kind of have an allergic reaction every time I see one of those solutions because I think it just takes so much time and effort to implement that in an interview. So I always stray away from it because typically there's a better way to solve it. Hope you guys enjoyed this. Hope you found it useful. Let me know in the comments down below if you have any questions, recommendations, or concerns. And I will see you guys in the next video. Peace.